me do that. Okay. Good morning, ladies and gentlemen. How are we doing today? We're doing? All right. We're doing. So, thus far, you have essentially been math-free for the week. That's about to change today. Okay. But what's nice is, it's all formula-based, and you get to do funny hand gestures. And so today we're going to learn about what's called the alternative right-hand rule. Okay, the original right-hand rule is where you...
Wasn't the alternative right-hand rule the left-hand rule?
No, because you're still going to use your right hand. So, as I may have mentioned before, I really like this chapter mainly because during tests and everything like that, I get to watch people do these little... Heck, they could probably be TikToks these days. I don't know. But it's very helpful when it comes to that those types of questions. So, over the next couple of days, we're going to be working on section 3. All right? It's been a fairly light chapter thus far. Okay? But it is time to get into some mathing. So what we're going to do in this section is, given the force on a charge on a magnetic field, determine the strength of that magnetic field. We're going to use the right-hand rule to find the direction of the force on a charge moving through a magnetic field. That should actually say alternative right-hand rule. And determine the magnitude and direction of the force on a wire carrying current in a magnetic field. Whew. A lot of words in those objectives, but it won't be that bad. Anyway, a charge that is moving through a magnetic field is going to experience a force that is going to be proportional to the charge, the velocity, and the magnetic field. So, formula sheet time. Get this formula up there. Where B is the magnetic field. Can anybody tell me what the magnetic field is measured in? Tesla, capital T. Yes. Magnetic field is Tesla. Magnetic force on a charged particle, is equal to magnetic force on a charged particle. Force being in what units? Newtons, I almost said it. In what newtons? Divided by the product of magnitude of charge in coulombs and the speed of charge, which is typically going to be velocity. Now, if you see here, we're talking force and velocity. What type of terms are those? What do they entail? What was that? Vectors. So when you are calculating for magnetic fields or forces, you got to make sure that you are including vectors. More so the force, okay? More so the force. Because Tesla is just a measure of the strength. So when if and when you are solving for force, you must remember to include direction. Okay? So, the direction of the magnetic force on a moving charge is always perpendicular to both A, the magnetic field, and the velocity of that charge. An alternative right-hand rule, there it is, can be used to find the direction of that magnetic force. A charge moving through a magnetic field follows a circular path. What path does it follow? Circular. Okay. Here's the right-hand rule. Go like this, like you're taking a pledge. All right. Coming out of your fingertips is the magnetic field. Coming out of your thumb is the direction, the velocity, therefore direction, of the particle. Coming out of your palm is the magnetic force. Okay? Now, extra cool points to you, if you can name that movie. Did we not? National Lampoon's Vacation. Very good. Wally World. Name the actor. Don Candy. Very good. Anyway, he's obviously practicing the alternative right-hand rule. Okay? It's just that simple. All right? But look what the little note I have above there says. And yes, you don't have these on your notes because I just put them on this morning. Like, what have I been doing these last few years? And not include this. I mean, it's perfect. Electrons, okay, are different. Mostly when we're talking about this alternative right-hand rule that we see here, that's where we deal with protons. Electrons differ in the direction in which the magnetic field is. Okay? With protons, the magnetic force. With protons, the magnetic force is coming out your palm. With electrons, the magnetic force is coming out of the back of your hand. Okay? So if you want to jot that down, it's also in your textbook. But protons, the magnetic force is out of the palm. For electrons, the magnetic force is coming out of the back of your hand. Okay? If you're like me, you grew up and your parents got the back of the hand. That was just me, them hitting me with their electrons, I guess. So, let's look at a practice question. Okay? A proton moving east. Now, for our purposes, we are not, these four walls are not perfectly square or flush in terms of cardinal directions. Okay? But for ease of that, this front wall is north, that back wall is south. Which direction is that? Yeah, very good. Which direction is that? West. East? I thought you said west. Where's that from? Yes. All right, I'm a kid. All right. So we have a proton moving east experiences a force of 8.8 times 10 to the negative 19th newtons upward due to the Earth's magnetic field. At this location, the field has a magnitude of 5.5 times 10 to the negative 5th Tesla to the north. Find the speed of the particle. What do we know? First of all, the charge was, it's in your book way back when. The charge of a proton is this value. If you want to write this value on your formula sheet, that's fine. 1.60 times 10 to the negative 19th coulombs. Oh. Anybody tell me what the charge of an electron would be? Negative that. Okay. So we know our magnetic field strength. We know our magnetic force. We need to solve for V. It is a negative 19. Right here? Yeah. Yes, it was a negative 19. So, oops. Going back to the formula we first saw and rearranging it for V. Again, did it just only ask for speed? Yeah. So since it only asks for speed, we don't have to include direction. Okay? But that's our thumb. So if we go back to the question. Okay, I'm going to come stand in front of everybody. Actually, I'll stand in front of the camera so they can see. I don't even know if they can see. A proton moving east experiences a force of 8.8 times 10 to the negative 19th newtons upward due to the Earth's magnetic field. At this location, the field has a magnitude of 5.5 Tesla to the north. Whew. Okay. Ready? Let's start using our alternative right-hand rule. So follow along with me. So one thing is the proton is moving east. Again, particles are our thumb. So which direction does it need to point? I don't know if your arm can contort that way naturally. All right. So our finger needs to be pointing to the right. Our thumb does. Okay. One thing is we also see is that the force, the magnetic force, is upward. For protons, where's the magnetic force come out of? Palm. So watch this. Whoop. Which way is my palm facing? Upward. Which way is my thumb facing? or east. And which way are my fingertips pointing? North. Isn't that what it says where the magnitude is going at, or the magnetic field is? So there you go. Just like that. What if it was an electron? Exactly. If it was pointing, if the electron is moving upward, my palm would be facing down. What's that? Yeah, you'd be going west. Yeah, you'd be going west. Okay. Don't open that window, Gage. Oh my gosh. All right. So now we get back to the formula, or the question at hand. And since we are only asked about speed, we do not have to worry about direction, although we could, because still going east. Basically, just plug in everything once you rearrange the formula for V, and you get meters per second. So again, run down the units for this formula. B is magnetic field in Tesla. F magnetic is force in newtons. Q is the charge of the particle in coulombs, and V is either the velocity or speed, just depends on which one they ask for, in meters per second. Okay? What I want you to do now is open up your book to page, I don't know. I forgot to write it down. Oh, no, that just means we get to investigate. It is page really far back. 689. I'm going to write that down. Page 689. Okay. Get off. Make some room, folks. Okay. All right, page 689. Let's look at number 1. So number 1, right here, says a proton moves perpendicularly to a magnetic field that has a magnitude of 4.20 times 10 to the negative second Tesla. What is the speed of the particle if the magnitude of the magnetic force on it is 2.40 times 10 to the negative 14th newtons? Okay. So let me get my board here. All right, so what do we know from number 1? We know, and I can't find anything up here. We know that our magnetic field, our B, is 4.20 times 10 to the negative second Tesla. We also know that our, I'm going to call F mag for F magnetic, is 2.40 times 10 to the negative 14th. Sorry, negative 14th. Thought that didn't sound right. Negative 14th newtons. And our Q, which we're, again, talking about a proton, 1.60 times 10 to the negative 19th coulombs. We need to figure out the speed. So again, taking our formula from before and rearranging it, you get V is equal to F magnetic divided by the product of Q times B. So what I want you to do is go ahead and solve for this. And then we're going to take it a step further. What? Okay, yeah. What do we got? What do we got? What do we got? Who would like to give me an answer? You.
6,000.
Does anybody else have something different? .57 times 10 to the 6th. Is that what people got?
Yeah.
Okay. Are you using parentheses?
Yeah.
Double check that. I've got one more that I want you to work on. And that is, did you get it that time? Okay. I'll leave it up here for a second. We're going to look at number 3. Number 3 says, as you work on that, a uniform 1.5 Tesla magnetic field points north. Okay. Let me get this back over here. All right. So uniform 1.5 Tesla magnetic field points north. If an electron moves vertically downward toward the ground with a speed of 2.5 times 10 to the 7th meters per second through its field, what force, both magnitude and direction, will act on it? Okay, so this is a situation where the right-hand rule comes into play. So what do we know? We know that our magnetic field is 1.5 Tesla north. We know that our charge this time is 1.60 times 10 to the negative 19th coulomb, because it's electron. And our speed is 2.5 times 10 to the 7th meters per second. Now, that's downward. I will say this. In terms of negative sign, it's not going to have an overall effect of direction or anything like that. So in reality, we could simply keep the negative sign out of the charge, okay? Because it doesn't play a role in changing the force or anything like that. Okay. In reality, in other realities, in chemistry, yes, it does have a negative sign. But for our purposes right now, mathematically, we can remove that because it doesn't have any bearing on our overall calculation. Okay. Yeah, you can just leave it as positive. Yeah. So find with magnitude and direction the magnetic force. You will have to use the right-hand rule. And yes, I will be asking for a volunteer to demonstrate the right-hand rule to the class. All right, what do you got there, window corner?
-6 times 10 to negative 12 newtons to the west.
Okay, so you had, and remember, I said you can remove that negative sign in front of that. So in actuality, it'd be 6.0 times what?
10 to negative 12 newtons.
Mm-hmm. West, perfect. Now, do I have anybody who would like to demonstrate in front of the class the right-hand rule? Okay, I'll do it. Okay, fine. about like doing the Macarena. All right. So I guess I'll turn this way. So going back to the question here, wrong class. It's not even on there, is it? It's in my book. Okay, if an electron moves vertically downward, and what force will act on it, and the magnetic field points north. So really, what do we say? I don't like having it over here. Magnetic field north, vertically downward. Yes. Oh my gosh, I cannot do this. Why can't I do this backwards? Oh, all right. All right. Magnetic field points north. Electron moves vertically downward. Okay. Is this how you had it? Like this? Or like this? Like there we go. There. Okay. Looking on there backwards is weird to me. All right. So again, electron is moving downward. Okay. Magnetic field pointing north. I'm burning up here. Therefore, the force for electrons is coming out of the back of my hand, and it is pointing to the west. Okay. So now it comes homework time because I'm sweating up here. I need to open the door. For today's homework, once you get this paper, I'm going to tell you what it is. I had a little rain melt up there.
We just need to do like one of these, right?
Oh, no, that wouldn't be nearly as fun. Now, I'll be honest, I can't recall how many of these require a direction, but I highly recommend that you practice the alternative right-hand rule as you go throughout these questions. Okay, because this will be, or you will have to do it for the test. Okay, so here are the numbers that you are to do. Question, yes.
This is turning Tuesday in class or not?
Yeah, I think I put it as Monday. Just make it Tuesday. Tuesday in class. Okay. So here are your numbers. Cross these numbers out so you don't do them. 4 and 7. Do not do numbers 4 and 7. All right, and for you at home, it should be posted online, so you can go ahead and work on that. I'm going to stop the recording and